Good and you.
Good.
Just happy for Thanksgiving coming up.
Not much. It's generally a pretty light week for me. Actually today is kind of busy, but the rest of the week's pretty light. So, yeah.
Nice.
So, what are we doing today?
Right now, I'm pretty much just reviewing all the chapter 5, all the stuff that I've done with you recently, I guess.
Okay. Do you have some review questions that are different than we've done?
Yes, I have some review questions.
Okay.
So what I noticed I needed to brush on were like the identities.
Okay.
So here's one. Sine 2x plus cosine squared x. One sec. And that's it. So it says simplify the use trig identities to simplify the trig expressions.
Okay. So what's sine 2x equal to?
Doesn't that equal 2 sine times cosine plus cosine squared x?
Now what can you do?
Factor out a cosine.
You have left
2 sine plus 1, and then
2 sine plus cosine x.
okay. Oh yeah, the 1 goes away. Okay, never mind.
Well, they didn't set this equal to 0, did they?
No.
It was just simplify the expression.
Yes.
No, this is the only way I know how to simplify it. I can't think of anything else we can do here.
Okay.
We at least have everything in x and not 2x. And even though we have a combination of sine and cosine, they didn't leave us much choice. Sometimes that's all the best you can do. If this was equal to 0, well, now I can set that equal to 0 and that equal to 0. And that actually might be a little tough to solve, but we could eventually do it. That's probably why they didn't set it up as a problem where it's equal to 0, just because they haven't really taught you how to solve setting that equal to 0.
Mm-hmm.
So this would be the final step. Okay, what else?
1 plus tangent squared x.
That's it?
Yeah, that's it.
What's the identity?
So what I do with the density?
What's the identity for that?
Does it have cotangent in it?
No, it's got secant squared.
Okay, secant squared.
That's what it is. It's equal to secant squared. Okay? The one that has cotangent is the third one. In other words, this is the second one. This is the second Pythagorean trig identity. What's the third one? This is the one you can figure out based on the second one.
Secant equals?
No. Use the cofunctions.
Oh, cotangent. And that would be secant?
No, the cofunction of secant.
Cofunction of secant. Cosine.
Cosecant.
Cosecant.
Okay,
yes.
Let's go over this, because I think I may have inadvertently confused you.
Okay.
Let's talk about this. If we're looking at reciprocal, not cofunction, but reciprocal, we always start there. And then we always have a problem as to whether secant goes with sine or does secant go with cosine. And what I always tell people is that make sure you have exactly one co in each relationship. Okay? There's the co, there's the co, there's the co. So as long as you know this one, and you know what the three predominant ones are, you can't really get this wrong. However, these are not cofunctions. Just because there is one co in each relationship, they're not cofunctions. Okay? Cofunctions are cofunction of sine is cosine. Cofunction of tangent is cotangent. Cofunction of secant, cosecant. In other words, cofunctions are merely the function with the word co in front of it, although certainly the cofunction of cosine is sine. Okay? So these are your cofunctions. And what property do they have? They all share this property.
90 degrees minus x.
Yeah, in other words, they're not reciprocal, but they do share a very interesting property. In other words, if I knew the sine of 30 degrees is equal to 1/2, well, this tells me that the cosine of 90 degrees minus 30 should be 1/2. If these two things are equal, and it's true, the cosine of 60 is equal to 1/2. So the cofunctions, although they're not the most important property, I've worked with people in trig that can go a long time before they even talk about cofunctions. Okay? They are not nearly as important as the reciprocal identities. And they are not nearly as important as the Pythagorean identities. And they're not as important as the quotient identities. In other words, there are 11 identities that are just absolutely imperative that you memorize and have them quickly at your memory.
Okay.
Then you get the cosine or the cofunctions. And the cofunctions are actually pretty easy. I mean, how hard is it to memorize? You stick a co in front of the sine. So, but don't get, in other words, this pair of relationships also has exactly one co in it. Notice. But cofunctions and reciprocal relationships are different. What is the third Pythagorean identity that we haven't written? It's actually the number one that they teach you.
Equals 1.
That's it. That's the one you get taught in Algebra 2 class. And you maybe don't get to these two until you take trig. Okay? But this is the one they really expect you to know. Even on the ACT and the SAT test. Well, not the SAT, but the ACT, they would expect you to know that one. I'm not sure they would expect you to know both of these. Okay? So, here's the 3 trig. There are 6 reciprocal identities. Right? I mean, we only listed 3, but if there's, in other words, if sine is equal to 1 over, what is it?
Cosine.
Cosecant. Then, out of necessity, cosecant's equal to 1 over sine.
Sine.
Okay? So, we really only memorize the 3, but we know 6 of them. And the 3 main ones, what kind of calculator did you have? I forgot. You said it had all 6 trig functions?
Yeah, 84. However, my teacher doesn't really let us use a calculator, so
all right.
that doesn't.
The only reason I mention it is that on all calculators prior to the TI Inspire, in other words, if you had a TI-84 or a TI-83, these would be the only three keys you would have. They don't put a cosecant key on there, they don't put a secant key, and they don't put a cotangent key. Why? Because if you know they're the reciprocal, it's pretty easy to take the reciprocal. Just take the thing and flip it, or divide by 1. Okay? So when I talk about the three primary trig functions, these are the three that I'm talking about: sine, cosine, and tangent. Now, in reality, they're no more primary than these three. These three here are every bit as important as these three. But out of necessity, when they were trying to restrict the number of keys they put on your calculators, they didn't want to put 6 keys. So they just put 3, and they chose these 3. So people tend to think of these as your 3 primary trig functions. And if you remember that, then you won't get the reciprocals confused with the cofunctions. Now, there's 2 others. There's the quotients.
Sine over cosine, cosine over sine.
That's 11. In other words, there's 3 reciprocal, there's 3 Pythagorean, there's 2 quotients, and there's 6 reciprocals. Those are the ones you want to have down pat. Most all problems involving verifying trig functions are going to use only those 11. Now, obviously, you've had others. You've had plus and minus. That's 2 more, 3 more if you count tangent. You've had double angle. That's 3 more. And you've had half angle. Have you not had half angle?
No, just double.
Just double angle? All right.
Yeah.
So let's go through them. First of all, let's do the sum and difference. And I want you to do this from memory. I don't want you to have these on a piece of paper that you can look at.
Okay.
Okay. When you're memorizing something, best way to do it is the flashcard method, where you have the answer handy, but you want to keep testing your memory on these. Okay. So to me, this is the easier one to remember. And I'm not sure why, but this is the one they start you out teaching you. They don't start out with sine. They start out with cosine. What's this?
I forgot.
Well, it's cosine, cosine. That's what I remember. And then I remember the signs are the opposite. It's minus, plus. That's all I have to memorize, because I know the rest. The rest has to be sine, sine. Okay?
Oh, yeah. Okay.
Now, what goes here and here? Well, obviously, A and B. It wouldn't make any sense to put A and A there. Okay?
Yeah.
And so what goes over here? A and B also. Okay? So to memorize this, you really only have to remember that it starts with cosine, cosine, and has an opposite sign in the middle. That's 2 things. Okay? Now, the reason they start you with the cosine is because it kind of helps memorize the sine a little easier, I think. The thing I remember about the sine, do you remember what this is?
Was it?
What's the sign in the middle going to be?
It's going to be.
It's the same. With sine, it's the same, so it's plus minus. You know what I mean by the opposite in this one, right?
Yes, you flip the sign from.
Yeah, in other words, if it's cosine of A plus B, then we're going to have this minus.
Negative.
Whereas this is the same. If it's sine of A plus B, we're going to have everything there plus everything there. Now, What else do we know? We know that both of these things have two sines and two cosines in them. So what does this have to be? If it's got two sines and two cosines?
Sine, cosine, sine, cosine.
Yeah. In other words, the only other case would be sine, sine, cosine, cosine, but we know it isn't that. Now you only have to figure out one more thing.
A and B.
And that's the same. Yeah. Well, you're correct. It's A and B. It could be A and A, but it's the same as that. In other words, remember it like that. This is A and B, and necessarily so. This wouldn't make sense if it was A and A. So if this is A and B, remember that this is the same thing, and this, therefore, has to be what?
A and B.
No, that would be the same
as
B
and A. B and
A. In other words, when I say it wouldn't make sense, if this was cosine A, it wouldn't make sense to write it like that. They would write it cosine squared A.
True.
Okay, so now this, the second one, for a long time I had difficulty remembering whether it was A, B, B, or is it A, B, B, A. And finally I realized, well, it's the same as cosine. And that's why they teach you the cosine first. It's easier to memorize, at least it is for me, and you can base the second one off of the first one. Fairly easy. Now, the tangent one. This was the hardest one for me, but it really shouldn't be. It's actually pretty easy to remember. The numerator is what?
1.
It's the same. Tangent A plus or minus tangent B. I said the same, almost the same. Okay. The denominator is 1 opposite minus or plus the product of those two things. Tangent A times tangent B. And like I said, this is probably the hardest one to remember just because there's a numerator and a denominator.
I don't think I need to know tangent.
Probably not. I wouldn't doubt that won't be on the test, but you definitely want to know the first two.
True.
And notice you can always figure this one out because this one is sine over cosine. If you put this and divide it by that and simplify, you get this. Although that simplification doesn't look real easy.
True.
It's not intuitively obvious to me why that would be the case, but it is. I've never had to try to do that. Okay. All right. So the last thing we need to go over is double angle. Right? In terms of your identities, there's no other identities that you need to know? You got the slope difference, you got the double angle, you said you haven't covered the half angle. Have you covered power reducing?
No.
You sure? Because I thought you had maybe one of those on the test. In other words, power reducing is kind of in a category all of its own.
I might be able to say yes or no.
Power reducing really is not used until you really get to calculus. Once you get to calculus, it's pretty useful. But what's sine of 2x?
2 sine times cosine.
Okay, good. And the tough one is the cosine one because there's 3 of them.
Sine squared times cosine squared.
It's cosine squared minus sine squared.
Minus.
Every one of these 3 identities has a minus. There's no products.
Okay.
Okay. This one, the second one, has only cosines and 1 in it. The third one has only sines and 1 in it.
The cosine, I believe, is 2 cosine squared x minus 1.
Good.
And then the sine is 1 minus sine x squared.
Now it's the same 2.
2 sine x squared.
Okay, so that's all you need to remember, is that all three have negative signs. This one has both cosine and sine. This one has only cosine. This one has only sine. And the reason there's 3 of them is we saw that there are lots of trig functions that when you go to solve, you have to convert this. And sometimes it's a lot more useful to have it all in cosine or all in sine than it is to have a combination.
Okay.
Now, tangent of 2 theta. Tell you an easy way to remember tangent of 2 theta.
Tangent x minus 1.
Well, tangent of 2x, we memorized what tangent of x plus x was, right?
Tangent x plus x.
Yeah, what is tangent of x plus x? That's the sum and difference. What would that be? Remember, the numerator is the same.
Okay, yeah, the numerator is the same. Then it would be a, tangent of a.
1 minus tan x tan x.
I think I have the other ones memorized, but not the tangent one.
Okay, but notice how we can figure out 2x. We know that the tangent of 2x is tan of x plus x. So it's got to be 2 tan x in the numerator and the same denominator, 1 minus tan squared x. In other words, if we happen to know the sum and difference, well, then this one is a piece of cake. 1 minus tan x times tan x, which is written like that. Tan x plus tan x is 2 tan x. But tan x times tan x is tan squared x.
Okay.
Okay? So even if you don't have this memorized, if you happen to have the sum and difference memorized, you can always get this one easily. And we could have done the same thing with sine and cosine, I suppose. But it's just easier to memorize these as they are rather than figure out what the sine of x plus x is and reduce it.
Okay.
All right.
One problem is sine 2x minus sine x equals 0.
Okay. On every one we've ever done of these, the first step is to use the double angle identity.
So sine, or 2 sine times cosine. Minus sine equals 0.
Now what? Now it becomes a factoring problem. All of these, yes, either they're quadratics or I can factor this thing into the product of 2 things. So if I take a sine out, what do I have left?
Then I have 2 cosine x minus 1.
Notice I have the product of 2 things. I have this times that. And since it's equal to 0, I can go in, and the next thing I can say is what?
So sine equals 0. Then I can use a unit circle, which will give me pi and 0.
Okay. Or?
And then it'll be cosine 1 over 2. Which will be pi over 3 and 5 pi over 3.
All right. You're being good on that unit circle is going to help you.
Okay.
No, it really is. I mean, that's a good ability to be able to translate that quickly and that.
Because I'm trying to figure out how to do this without freezing up, because I get it really easily when I work with you, but then sometimes in class, like, I just choke.
Yeah, no, that's not that uncommon of a phenomenon.
It's really irritating to me.
Yeah, no, I know what you're talking about. Same thing in any subject, sport, or anything else.
Uh-huh.
It's just when you're under a little bit of pressure, it's just harder to access your memory as easy as it is when you're comfortable and relaxed.
It's really frustrating.
Yeah.
The next one I have is cosine 2x equals cosine x.
Which identity am I going to use?
2 cosine squared x minus 1.
Yes. Why?
Because I want to keep it with the cosines.
If I can, I want to turn everything into the same trig function. I already got a cosine over there, so if I can turn that into nothing but cosine x, whether it's squared or not, I'll be fine. So 2 cosine squared x minus 1 equal cosine x. Now what?
And then would I bring cosine x on the left side?
In other words, at this point, treat it like a quadratic, just like a polynomial. Just like we did the last one. Just like we did the last one, only the last one, we didn't have to factor it like a polynomial. We were able to factor a greatest common factor out. Well,
True.
This is a little different. There's no greatest common factor, but you'll notice that it's just like a polynomial. In other words, it's like a typical quadratic. How does this factor?
I don't factor out a cosine.
No.
Oh, never mind. 2 cosine plus 1.
X, yeah. Don't forget the x. I know I tend to sometimes, but when we're doing these, it's important that you use the x.
Okay. Then cosine minus 1, and then I have to check the middle term to see if I'm right.
Okay, so to check the middle term, just multiply the insides and the outsides, add them together.
So negative 2 cosine x minus 1 cosine x. So yes, it's right.
Okay. In other words, you don't need to do the entire FOIL. You just need to do the inside and the outside and see if that is the correct term. If you're off by the sign only, then the simple remedy is just to switch these numbers.
Okay.
Okay. So sometimes you use that method to even determine whether you're in the ballpark, if you're close or not.
Okay.
You know what? See how fast you can do these.
Next one I have is...
Well, no, finish the solution.
Oh.
In other words, notice that we're not solving for angles here. We will, but we're initially solving for cosine x.
Mm-hmm.
So what's the first thing cosine x can be equal to?
Negative 1 over 2.
Now we're solving for angles. That's why I was kind of insistent that you put the x in there, that you don't leave it out. Is because ultimately with these problems, we're solving for x. We're not solving for cosine x. We're solving for x. Where does that occur?
Then that occurs at 2 pi over 3. And I believe 4 pi over 3.
Okay. Second one?
Then that would just be cosine equals 1. And that would be 0, and that's it.
Huh. Okay.
Next one I have is...
So do you actually have this thing memorized? I mean, did you actually memorize all spots on this thing?
After I draw it out, I can't just whip it off from my memory, but after I draw it out, like I can draw it out easily, but I can't just
I don't
think
have
of,
all spots memorized.
yeah.
That's not the way I do it. I memorize the first quadrant only, and then I know this one is 180 minus theta. This one is theta minus 180, and this one is 360 minus theta. Okay, so if you say what's the cosine of 120 degrees, plug 120 in for theta, that's the same as the cosine of 60, which is equal to 1/2, but it's in the second quadrant, so it's that. That's the process I go through every time. I'm impressed that you appear to have it memorized. They want you to memorize. I just am not sure I've ever met anybody that actually memorized all 16 slots. Because that's how many you get if you take that unit circle and divide it up. You get 16 different points. And they want you to memorize all 6 trig functions at 16 different points. That's 96 things they want you to memorize.
Like I have it memorized as long as I can draw it out. Like I can draw the unit circle.
That's what you need to be able to do. That's better to me. I wouldn't want anybody to memorize all 96 things. I think that's a waste of a way to do it.
True.
The best way is, yeah, well, if you can do the first quadrant, I can figure out the second, third, and fourth. Because all I need to do is have the first quadrant memorized. And I don't even memorize the first quadrant. What I memorize are these 2 triangles and these 2 graphs. With those things memorized, that is about all you need.
Okay.
Notice that this gives you the answer to all first quadrant angles, and these 2 give you the answer to all quadrangles, multiple of 90s, 90, 180, 270, and so forth. But between what you're looking at on the page here, now you obviously need to know how to quarter that up, but as long as you remember that goes to 2 pi, the rest of it will take care of itself. In other words, you can't quarter it up incorrectly if you know that it goes to 2 pi, 1 cycle.
Okay.
So between everything you see on just this page, you can do all first quadrant angles that are the common ones. And then between what I drew in that unit circle and this page, you can do any angle that I give you, that is as long as it's a multiple of 30, 45, or 60. That to me is the way to memorize anything in groups. Groups of 3 or groups of 4. You know, if I gave you a 16-digit credit card to memorize or phone number or something, you'd memorize it just the way you memorize a phone number. That's why we break it up into
pieces.
Yeah, exactly. It's easier. The human brain doesn't memorize stuff beyond 7 items very well. And they've actually determined that 7 is the magic number. That's why phone numbers are 7 digits without the area code. Anything over 7 becomes more tougher for humans to memorize.
True. The next one I have, like, I think these problems are really easy, like, looking at it. I just think I just was confused at the time.
Yeah,
Okay, but,
and these problems are problems that we've done.
yes.
Would you like me to find some that are a little tougher?
I have some ones that I haven't done in a while that I think would be good to go over.
Okay, I have some not that much tougher, but a little
Okay.
tougher. Let's just do 1 or 2 of these. I hate to stick with the super easy ones and doing them a second time. I mean, if that's all you're going to get in your test, that's different, but instructions here are not to solve for x, but to prove this identity. First of all, question. What if it was solved for x? What's x equal?
I have no idea, to be honest. I just know the
anything. All reals. Because this is the basic identity, right? In other words, that's the first one. Cosine of 2x is equal to cosine squared minus sine squared. This thing is true regardless of x. And what that means is it's true for all x. Okay? If I wanted to prove it with some degree of difficulty, I suppose I could do something like 2 cosine squared x minus 1. And now instead of cosine squared x, I'm going to put 1 minus sine squared x. You with me?
Yes. And equals cosine squared x minus sine squared x.
Interesting. It's not that easy to prove that way. Unless I'm missing something. Let's see, it's also equal to 1 minus 2 sine squared x. Yeah, you know what you have to do here is substitute for that. In other words, 1 is sine squared x plus cosine squared x. Now I'm saying minus 2 sine squared x. Is that all equal to that? And yes, it is. Sine squared x minus 2 sine squared x is minus sine squared x. So this whole thing becomes cosine squared x minus sine squared x.
Okay.
But this is a weird first problem because it's not very often where they give you the identity and they say, prove it. In other words, I could do this in one step. So all I have to do is substitute this identity for that over here on the left. And now I've proven that the left side is equal to the right side.
Okay.
So that's kind of a squirrely one. And I thought I was giving you a little bit tougher one, but I wasn't.
Next one I have is
Okay.
sine x minus sine x cosine squared x.
Just that?
Yes.
No equation?
Nope.
Okay. How are we going to simplify this expression?
What I do, 2 sine x times cosine.
Always be factoring.
Factor out sines.
Exactly. In other words, if you see an expression that can be factored, almost certainly you should factor it.
Okay.
That's when you're looking at an expression or even an equation, set that equal to 0 and it doesn't really matter. I'm still going to factor it. Okay, so always be thinking factoring.
Okay.
So factor this.
I'll factor out a sine. And that'll just bring me cosine squared. Or cosine squared x minus 1, right?
Oh, almost.
1 minus cosine squared?
Yeah, know what factoring out is. When you factor out a sine x, you're dividing that by sine x and that by sine x. And what's left is what you get. That divided by that is 1. That divided by that is cosine squared. Okay? So that's what you're doing when you factor something. Is you're merely dividing both terms by whatever that is. Now, well, I can do more stuff here. What's 1 minus cosine squared x equal to?
2 cosine.
No. Here's the one, yeah, this one you want to be able to recognize quickly because you're going to see it the most.
I need to go over those identities.
Well, let's go over it. Now, you're probably not going to see it like this. They're not going to give you a test and say sine squared plus cosine squared. What they're going to do is they're going to give it to you like this. They're going to alter this. So they'll give you identities where they give you that. And you have to recognize that that's the same as sine squared x. And 1 minus sine squared x is the same as cosine squared x. So the goal usually is, gosh, I can replace two things with one. Same thing down here. If I ever am looking at 1 minus sine squared, I can replace it with cosine squared. This identity is the most important one, for sure, of the Pythagorean ones. And be aware of it in all of its alterations. So if we go back up to this problem, 1 minus cosine squared, that's the same as sine squared. Now what's this equal
to? Sine squared x, yeah.
What's sine x times sine squared x?
Sine cubed x.
Okay. Yeah, these trig identities are bizarre. I mean, when you look at this, you wouldn't think that that's the same as sine cubed x. So it's hard to figure out what they are. You just kind of have to follow your nose and follow the direction. But always be factoring, if you can.
Okay.
There's an expression they tell salesmen, ABC. They teach every salesman, no matter what product you're selling, they teach you ABC, and it stands for always be calling. You'd think it would be ABS, always be selling, but oh no, it's always be closing. I got it wrong. It's always be closing. Whenever you're with somebody you're trying to sell something, forget everything else and always be trying to close the deal. That's what ABC stands for. All right. Okay. What else in trig?
Another one I have is, one sec. Sine x times cotangent x.
Okay.
So would I turn that into the quotient property, the cotangent?
Okay.
Sine times sine over cosine over sine. Then the two sines would cross out, and then it would just be cosine.
Yep.
Okay. 2 sine times cosine. 2 sine x times cosine x.
What's that equal to?
2.
No, that's an identity. The double angle identity.
Double angle identity?
Huh?
1 second. Okay, there.
You want to make sure you know these identities, not just left to right, but right to left also. That's the sine of 2x.
Okay.
You know what I mean by right to left? Not just
yes, because normally I turn sine 2x into that.
You knew sine of 2x. I know you did. We've had it 3 or 4 times today, and the last 3 times you got it first right off. Okay? But you didn't immediately recognize that as being the sine of 2x. And that's what's helpful, is if you can recognize it both ways.
Front and backwards.
Yeah, front and backwards. Just like all math. I don't know of any math that they don't want you to be able to go in both directions. If you know an expression expressed exponentially, they want you to be able to express it logarithmically. If something's expressed logarithmically, you want to be able to express it exponentially.
Okay. Next one I have is 1 minus 2 sine squared x. And knowing that backwards, would it be cosine 2x?
Yep. Good.
Dang, that's a free one. That's not bad. Okay. Tangent sine x plus cosine x. Not squared, not squared.
Okay.
So what I do, sine over cosine times sine plus cosine. So it would be sine squared over cosine plus cosine over 1. And then common denominator.
There you go. What's the next step once you get there? Because that doesn't have to be the final simplification. But you have to kind of be a little perceptive here.
Could I cross out the cosines?
No, cannot factor out the cosines. But I can add these two things. You had the right idea when you said put it over a 1 and then find a common denominator. What's
So multiply the right side by cosine. That would be
this will become what?
Squared cosine.
And then I got sine squared plus cosine squared. That will become what?
1 over cosine.
Exactly. So,
and that equals,
so the first step, let's do it. Just make sure you saw everything we're doing. So far we haven't changed anything. Whenever you're doing this, almost from step to step, make sure that everything's the same. I haven't changed anything at all. Okay, now I can add the numerators, which is 1. Denominator stays whatever the common denominator is, but that's not our answer. What's our answer?
sine.
No, reciprocal.
Secant.
Secant. There's one co, but sine does not go with cosine. Those are cofunctions, but they're not reciprocal functions. And that's actually, if you had a TI-84 calculator, it would actually help you. It would be like a mini cheat sheet, because you would know that those are your 3 predominant trig functions. And if you know those 3, then you know that cosine can't be reciprocal to sine.
Okay.
Okay. So it's kind of helpful if you think of these as the 3 predominant trig functions. And you can kind of base everything else off of that.
Okay. The next one is 1 minus sine squared x over cosecant squared x minus 1.
Oops. Okay.
I know the top will be cosine 2x. I know the top is.
No, but you're close. Oh, cosine squared x, which is different than cosine 2x.
Oh, I was thinking about that. Yeah, I was thinking about the identity, but there's no 2.
Exactly.
Yeah,
if it was that, then it would be the cosine of 2x. But when it's just that, remember your primary identity is sine squared plus cosine squared equals 1.
Yes.
Now, what's the identity involving cosecant and being squared?
Tangent?
Tangent goes with secant. Always remember that, because one day you'll take calculus and the derivative of tangent is secant squared. So tangent and secant kind of go together. And it's not a bad way to think of them like that. Okay. Now, there's a third one. What's the third one? Remember I said that you have to memorize this one, but the third one you can always figure out by using the cofunctions.
Yeah, there's sine is...
what's the cofunction of tangent?
That would be And let me think.
Remember what definition of cofunction means?
Cotangent.
Yes, you take the function and you write the word CO in front of it. It's that straightforward as that. That's what cofunction means. You write the function and you write the words. In other words, I write tangent and I write CO in front of it. So it's cotangent. Only we don't generally write all 5 letters. So cotangent squared of x plus 1, what's it have to be equal to?
Secant?
Cofunction of secant?
Cosine. Or cosecant, my bad.
Notice how the bottom one is similar to this one. Doesn't get memorized. It just needs use the cofunctions of everything you see. Okay. Now that we have the bottom one memorized, what is cosecant squared x minus 1 equal to?
Cotangent squared minus 1?
No, just cotangent squared.
Okay.
In other words, if you do the algebra, all these are is algebraic manipulations. I'm going to subtract 1 from both sides. I'm left with cotangent squared of x equals cosecant squared of x minus 1. And since this is what we were given, I'm going to substitute one term for it. So cotangent squared goes there. Now, what can I do? What's cotangent squared equal to? In terms of cosine. In other words, I don't tend to think of turning cosine into cotangent, right? I mean, who does that? But a lot of times you turn cotangent into cosine and sine. What's it equal to?
Sine over cot.
That's tangent.
Cosine over sine.
Cosine squared over sine squared. Now simplify.
Would I cross out the cosines?
Uh-huh.
So now just leave me with sine on the right.
Sine squared in the numerator. I'm a little nervous about saying, yes, you can cross out the cosines. You can cross them out as long as they're both in the numerator. If you have them in the denominator, say I have 1 over cosine all over tangent over cosine, I can't cross those out. Well, hold on a second. I got this backwards. I can only cross them out. Well, regardless. I mean, because of that, I don't like to think of crossing them out. The way I'm doing this problem is I'm flipping the denominator and I'm multiplying. That's the way I'm doing it. So it's going to be cosine squared x times sine squared x over cosine squared x. Now you can see exactly what you have. It's easy to make a mistake if you do it, if you happen to come up with just trust me. You're better off flipping and multiplying and then going with that answer.
Okay.
Yeah. So here's another one you want to recognize. When you see that, know that, first of all, when you see anything squared with a 1, you're looking at a Pythagorean identity, almost always. They may have algebraically manipulated it. In other words, this thing started out cotangent squared plus 1 equals cosecant squared. But after manipulating it, this is what you see when you run into an equation. So again, you have to remember the original identity and know its manipulations also. It's not just knowing left to right or right to left. It's knowing the manipulations. And when I see any trig function minus or plus a 1 or 1 minus a squared trig function, I'm thinking, which Pythagorean identity is that? As opposed to if I just had that, now I'm kind of thinking I'm not going to use a Pythagorean identity. I'm going to use a quotient identity. That's cosine over sine, and that's 1 over sine, squared in both cases. But in other words, you look for clues as to which identity you're going to use.
Okay. Can you go over all the manipulations? Since I feel that I know this, but the only problem with me are the identities and switching them to things like that.
Okay. We have 5 minutes. Do you know the 6 reciprocal identities? Here, I'm going to put them in, you match them up. Just a second. What's the reciprocal of each one of these 6?
1 over cosecant, 1 over secant, 1 over cotangent, 1 over cosine, 1 over sine, and 1 over tangent.
Okay. Notice that the tangent is the only one that has the same reciprocal as cofunction. In other words, cotangent is not just the reciprocal of tangent, it's also the cofunction. And none of the others can you say that about. What are the 3 Pythagorean identities? Ones involved squares and ones. First one.
Sine squared plus cosine squared
Equals?
Cosine 2x.
Equals 1.
Oh, equals 1, yes.
Okay. What was equal to the cosine of 2x? Something close to this, but not this.
Oh, would it be minus?
With the cosine in front.
Yes.
It's cosine squared minus sine squared.
Okay.
That's one of them for cosine of 2x. What's the second Pythagorean identity? Involving tangent.
Tangent squared x minus 1 equals secant.
Plus 1.
Plus 1 equals secant.
Squared.
Then cotangent.
All of your Pythagoreans are squared. There's nothing that's not squared here.
Okay. Then cotangent squared x minus 1
plus
equals
1. It's the same.
Okay, that was plus. Okay.
Equals what?
Cosecant squared.
Yeah. Now, notice these are kind of fundamentally different, all 3 of them, in the sense that here I'm adding 1 to tangent to get secant, whereas up here I'm adding sine to cosine to get 1. And in fact, if I turn these around, cosine squared is going to equal 1 minus sine squared.
Yes.
Whereas secant squared minus 1 is going to equal tangent squared. And cosecant squared minus 1 is equal to cotangent squared. So here's what you're looking for. You're looking for stuff that looks like this, or looks like this, or looks like this, or looks like this. Each of those has a single term identity.
What do each of those equal?
Well, what's this one equal?
1 minus cosine squared. That would equal cosine 2x?
No.
Or no.
There's 3 identities. Just manipulate them algebraically.
I'm thinking sine.
No. How do I get 1 minus cosine squared? I subtract cosine squared from both sides.
Yes.
What are you left with on the left?
Let's subtract cosine squared. On the left, I'll have 2 cosine squared x.
No. I'm going to subtract cosine squared from both sides. So now 1 minus cosine squared is equal to sine squared.
Yes.
So this is the same as sine squared. This over here is the same as cosine squared. This down here is the same as tangent squared. And this down here is the same as cotangent squared. And as all I'm doing is taking these 3 fundamental identities and moving one term to the other side of the equation.
Okay.
Okay. Taylor, I got to run. I got a 3:30.
Okay, I might sign up for another 30 later on.
Yeah, that's fine.
Okay.
All right.
Talk to you later.
Have a good one. Bye-bye.
Thank you. Bye.